Bismillahirrahmanirrahim. Assalamu alaikum. In today's lecture 18, we will discuss the vertical curve fundamentals. So, what are those fundamentals? If you have a crest curve in which a G1 upgrade meeting a downgrade G2, you can always find the elevation along the curve using this equation. And since this is a parabolic curve, so you can also say this equation can be applied to this curve. Y is equal to, this is the general equation of parabola. So if in order to find any elevation, we know that y is equal to ax square plus bx plus c. And if we have the origin at PVC, and this is always my x, the minimum value of x is 0 and the maximum value is the length of the curve. So the x can be 0 and x can be as large as L by 2. Then the coefficient A can calculate it very easily using the curve fundamentals. You can find the value of A as G2 minus G1 divided by 2 times length of the curve. And mind you, G2 and G1 should be in percent. Then the coefficient B is simply G1. So for instance, if G1 is say 2%, it will be 0.02 and so on and so forth. Remember, if this is a sec curve, then this G1 can be have a minus value as well. This equation is a general equation either for a sec curve or a crest. So it's, you don't need to get confused whether this equation is valid for sec curve or not. Another thing is the distances, or what we call the offset distance between the curve and the tangent. Since this is the tangent, so any point, any distance between the curve and the tangent, we can call it an offset. And the general equation of y at any point along the curve is simply y is equal to a upon 200L times x square. Again, you know what is x. And if so, you can check this equation if say x is L by 2. So obviously when x is equal to L by 2, y becomes ym. And we can use simply ym is equal to, if I put x is equal to L by 2, this can be easily translated to AL over 800. Now, if I'm talking about x is equal to L, then this becomes the final value of the curve, final offset of the curve at the end of the curve. So this we called as offset at the end of the curve. And simply how we have found this AL upon 200 is simply we have replaced XBL and just simple application gives this AL upon 200. So these are the basic concept. Another thing that is missing is that's importantly used for calculation of the length of the vertical curve is the highest point and the lowest point. Now the highest point and the lowest point can be determined by just using this equation that XHL. So if it is a crest curve, then it is the highest point, and if this is a sag curve, then it is the lowest point. So this XHL is equal to K times G1, and we also know from our previous lectures that K is always length of the curve divided by A, where A is the absolute sum of the grades. When we say absolute, I mean, for example, if it is 2% meeting 3%, the value of A is simply 5, right? So we have to always add it, and we are not, we just ignore that, you know, the percent value, simply the absolute. And as we know that we have this K is dependent on the side distances, and these K values can always be found, and it is also, sorry, it is also dependent on the design speed. And obviously uh, we have a tables in the policy of geometric design of highway, that is a green book, where we can always find K for crest curve and K for sag curve uh, for a particular design speed. Now, in order to understand fully the fundamentals of this curve, we are going to solve three problems in this lecture. So our first problem is about solving the sag vertical curve. Uh, the problem statement is that an equal tangent sag vertical curve has an initial grade of minus 2.45%. It is known that the final grade is positive and that the low point is at elevation of 270 feet and a station of 141 plus 00. The PVT, that is the termination of vertical curve, is at elevation 274 feet and the design speed is 35 miles per hour. Our objective is to determine the station and elevation of the point of commencement of vertical curve, that is PVC, and point of intersection of vertical curve. You know, from the statement, since it says that there is a minus 2.5, obviously there is a downgrade, and it is said that the final grade is positive, so that it means the downgrade meeting sag upgrade. That's why I say this is a sag curve, and now we need to solve it. First, we'll find out K, and from the green book we know that for sag vertical curve having a 35 miles per hour speed, we know that K is equal to 49. Since from the curve fundamentals, we also know that the high point or the low point of the curve is simply K times G1. K we already got from the table. G1 we know, and this becomes 122.5. Remember, as we were knowing those curve fundamentals, as you can see over here, this G1 value is absolute. That means it will be always positive. Since the distance cannot be negative. So even if you just doesn't notice that this is a mode, you just have to ignore the sign of G1 while calculating X. So we calculated X, and since we know the elevation of the low point and the distance of the low point, we can always find the elevation of the PVC from the basic equation. Here, so the equation is simply y is equal to ax square plus bx plus c. X we know is 122.5, and then we know a is g2 minus g1, but unfortunately the problem here, we cannot find the value of a because we don't know L as well as G1, but we don't know that G2 minus G1 is capital A, and we also know L is equal to K. This is the relation that we are going to use. So, and G1 is obviously minus 2.5. So here B will simply require plug in the value of 2.5%, that is 0.025. We know the elevation Y, that is 270. So what we are going to do is simply, we know that L is A, that is the basic relation we know from the fundamentals. And since A is equal to G2 minus G1, so what I have done is replace G2 minus G1 is capital A, and I have replaced L is equal to K. So definitely we will find that the value of A becomes 0.0001020, just from simple mathematics. It's nothing, it's just a plug and place value. And then if you put it in the fundamental equation, we can find the elevation at the beginning of the curve. Sometimes, we always get confused about BVC of PVC. It's same. From BVC, from some literature say it's BVC, it's the beginning of vertical curve. And most of the literature say it's the start of the commencement of vertical curve. So either we say PVC or BVC, it doesn't matter. So once you know the station of, we already know the station of PVC, so we'll find the value of the station of PVC. The elevation of the PVC is can be known to us, and since we know the length of the curve, since we know that the elevation of the point PVT is 274 feet, so again we use this equation where we say 274 is equal to 0.000102 times L square. We have replaced x with L. We can always solve this equation to find L is equal to this one. And since we want to find A, we know K, we know L, therefore we find A, and consequently, once we find A, we find T2. Simply, so now what we need to do, everything is solved. Now, if you want to know the elevation of PVI, it's simply elevation of PVC minus G1 times L by 2. Just plug and will plug the values, and you will get to the value of the elevation of PVI. And obviously, the second part says that we need to find station, simply the station of PVC plus L by 2, and that's 139,775. We already calculated here the station of PVC. So we are going to put it here, and we'll find the station of PVI, and last but not least, we'll find the elevation of PVI. Simply, we know that PVC of elevation plus G1 times L by 2, but since G1 is negative, so this will be this. There is some basic concept while calculating the elevation along PVI or PVC. If it is a sag curve, you must remember that the elevation of PVI should be less than the elevation of PVC because it is a sag curve. But it is inverse, it is reverse in the case of elevation of PVC, because if we know the value of PVI, then we always going to add this value of the grades so that the elevation of PVC is above than the elevation of PVI. Conversely, if you are calculating the value of PVI of a crest curve, then obviously the elevation of PVI of a crest curve will be higher than the elevation of PVC. This problem is meant to broaden your concept about how to use K values. As this is not enough, we'll solve another problem that is it's also a real time problem. It's a very problem, and you often come across while you are designing a bridge in which you are joining the elevation of your road level and the elevation of the bridge. So the next problem will give you the concept about that. This is this is 3-36 at this page 307 of your book. Now let's see another problem in which there is a tunnel need to be connected to a newly constructed bridge with sag and crest vertical. We can see this profile view from the figure. I will show you after this slide. We need to develop a vertical alignment to connect the tunnels and bridge by determining the highest point common design speed for the second vertical curve, compute the stationing and elevations of PVC, PVI and PVT. So this is a very interesting problem. Now in this problem, obviously this is a tunnel and this is a bridge and this is a transition between each of this. The bridge is at higher level, the tunnel floor is at the lower level. And 100 feet below and station is, and the difference between the elevation, the bridge deck elevation is 140 feet. Notice that we have not been given any grades. And again, by using the curve fundamentals, we'll find those grades, and once this grades is known, we will easily find all the curve parameters as been asked in the problem. So we see from left to right a sag curve. We have subscripted it as S, and a crest vertical curve we say C are needed to collect the tunnel and the bridge. So this is a sag curve and this is a crest curve. This is downgrade meeting the upgrade, and this is the upgrade meeting the downgrade. Remember, this downgrade is 0%. Yes, it can be. But downgrade can always be negative. It can be 0 as well. Right? So a sag vertical curve from the given information, we know that obviously G1 here is 0, and similarly G2 here is also 0 because they have no slope at all. So this is the final slope. To obtain the highest possible design speed, we will use all the horizontal distance available. So we say this means that we want to connect a curve so that the PVT of the sag curve will be PVC of the crest curve. So if this is the case, G2S is simply G1C and G1S is G2C is 0. And obviously this becomes A as absolute sum of the grades for sag curve and vertical curve. They are equal as well because one of the value is 0 and G1 is common. You see here, this G1 is grade. This grade is common to both of the curve. So that's why this is G1. If I add this G2 and G2 is 0, so again this A is G1 plus G2 and this becomes A because G2 is 0. Similarly, for the crest curve, again I will add A. This is G1 and G1 plus G2 and again G2 is 0. So that's why the absolute value of sums of sag curve as well as crest curve are equal. That's why we can say is simply we can use this mathematics. So we say AS is equal to AC. Now, so we know that from fundamental K is equal to LA. So we can write LS AS plus LC AC is equal to 200 because okay, we will do it like this. Let me say, but the length of the sag curve and from the sag curve is 1200 feet. How? This station is 1200. This is the start of the curve. This is the termination of the curve. So the length of the curve between this distance, the distance between these 2 points are 1200. 1200 minus 0. That's why we say length of the sag curve plus length of the vertical curve. It is not going to go beyond 1200. This is the maximum value as we can understand from the figure. So this is a leg. Again, we know that the curve fundamentals, that any value along the curve, because this is the end of the curve, this we can say this is YF, this is YF. If you this is YF is common to both of them. Uh, I just remember what is YF here. This YF is this point. So YF is common for both of us, both of this curve, and this is simply AL over 200. So we'll say what we can say that this ALS over 200 plus ALC over 200 is 40. Why 40? Because the elevation here is 140. The elevation is here is 100. So the difference in elevation between the tunnel floor and the bridge deck is simply 140 minus 100, that's 40 feet. And that's why I've written here as AL over 200 plus ALC over 200 is equal to 40. Now, again, we use simple mathematics. If you take out A upon 200 common and we find that LS plus LC is 1200, then we can always easily find out the value of A, that is 40. Now, as we know the A, we can always find the value of Ks and Kc. Why? Because A is known to us. We know KSA plus KCA is also 1200. This is our fundamental curve. Length of S curve plus length of test curve is 1200. And we know A is equal to 12, 6.667. So we find KS plus KC is equal to 80. Now, to find the highest this possible design, we say we need to know we have to take the value of K, S and Kc in such a manner that it becomes the total becomes 180. So this is a trial and error. What we take one design speed, say for instance we start with 30 miles per hour. So if we say for 30 miles per hour, K required is something, say 70, and for the same value of desired speed for crest sag curve, we'll find K as say 40. So if I add 70 plus 40, this becomes 110. So this is not going to solve the problem. So with our using our intuition, using our guess, we compromise in one speed that if we add these value of Ks and Kc, this becomes 80. Fortunately, this is actually this is 180. Pardon me for this typo error. So the we say that if you take 50 miles per hour, Kc becomes 84, Ks becomes 97, 96. So it's totally 180. So once you know the value of Ks and Kc, you always find the length of the sag curve and the length of the crest curve. Now the problem becomes now much easier. You can understand. Now you must realize what what is why we need the fundamentals knowledge of the curve. So by using this fundamental knowledge, we can always solve complex highway problem like this. We'll just with a few equations and assumptions. So we know this curve, and once we know this curve, then you can always find the station of PVC. So we will say that PVI will become this thing, and PVT, and this becomes only now the trivial values, and finally we'll know the elevation of PVT and PVC by using simple geometries. So this is how is using curve fundamentals you can always combine sag curve and vertical curve. Now we move on to the next problem. This is the last of this alignment problem in which we want to solve horizontal and vertical curve simultaneously. Now the problem says a two-lane highway has a posted speed of 50 miles per hour, and on one section it has both horizontal and vertical curves. Uh, a recent daytime accident shows resulted in a fatality, and a lawsuit against the department has been filed, alleging that this posted speed is an unsafe speed that should not be have been posted, and the accident has happened because the driver was careless and he was confident that this 50 miles per hour speed is adequate, but unfortunately that doesn't happen, and this is the design fault, and obviously the department has to pay for the compensation. Now, what you can see from this problem, this is the PC station 16, and this is PT station. Now this is obviously the plane, and this is horizontal curve. Then there is a super elevation 8%. There is a distance M 18 feet. Actually N is taken from the center line, so M is actually 24 feet. This is a 18 feet offset of the obstruction from the edge of the roadway. Obviously, if I add 6, this becomes 24 feet. There is a deflection angle 80. And if I look at the profile view, I can see that this is a curve G1. Pardon me for that. Let me, paste this equation higher so that you can see. So this is a grade G1 minus 2%, meeting a grade G2 is equal to 4%. There is a station at PVC 14 plus 00, and the station PVT station 18%. And in a short while, we will see how these values can be used to solve the problem. First of all, we know all these parameters, and we also know the length of the curve, so we know what should be the radius of the curve by simply plugging in this simple relation to calculate radius. This is 180 pi delta L. All of these things have been given, so this is the radius we found. Once the radius of the is found, obviously we will be uh, will say the we can always use this equation for super elevation. So this is 50 miles per hour. We know Fs, so we'll find that this Fs, and if you just use this equation, that super elevation equation that we know before, we can find Fs that was required, and Fs that was provided. Right? So this means that this provided Fs was greater than the required Fs, so that curve radius was adequate. Similarly, we know this one adequacy, we know that our super elevation was adequate because we find Fs, and then this offset distance we can always find safe stopping side distance using this relation we already know, and we find that safe stopping side distance required is 479.8. Remember, R we have calculated for simply subtracting -6 from the RC we calculated, and obviously MS was given 18, but we have added 6 feet, so it becomes the center of the bound length, so that's 120. And if you look at the required SSG, it was 425 feet. The provided SSG is 479.3 feet, so there seems no problem in the design of horizontal curve, and we can safely say that the horizontal curve was adequately designed on tubal test. Once we know that the value of Fs, it is okay, and the side distance. Another way, if you're confused about this Fs value, just forget and try to find a radius from the simple equation. And you will find that the radius you have provided in this equation, simply using the basic equation v square of 15e plus Fs and using Fs as 0.14 using from the table, and you will find radius that will be was the radius that was required and the radius that was provided 1198 is adequate enough. And secondly, you can always find that the object, the offset or the building was adequately placed, and that's why you calculated safe stopping side distance. Again, if you go what was required for safe stopping side distance and what is there, so we'll say there is no problem with the curve. Now we move on whether that vertical curve was designed adequately or not. So we know that A is equal to 6%. We know the length of the curve simply because you can see that, pardon me, this 18 plus 80 minus 14 is 440 feet. So 480 feet, and so we'll find K. Now, if you go back the table for the sag curve, we'll find 50 miles per hour. The K value is 96. So this means that the curve was under design, and this need to be corrected. But but the highway department will still not pay for the compensation. Why? Even though we admit that the project vertical curve was not adequately designed, but the value of since the accident occurs on the daytime, so there was no sight distance problem, though there was no vision problem. That's because even if the length of the curve was inadequately designed, still the accident did not happen because of that length of the curve, right? So this is another problem. So this is it for the fundamentals of geometric design. I hope you fully understood this problem, and um, you will be able to solve the problems related to vertical curve. Thank you very much uh, for listening to this lecture, and I hope you have understood the lecture and the concept behind those lecture. So that's now I'll finish this chapter, this fundamentals. So we will be starting the live section now. So if you have any questions, please feel free to ask.